In this topic, I will present you some of the laboratory tests that can be performed to infer rock material strength. It is important for you to know what type of tests can be done and what type of information we can gather from them. The simplest test to perform is the unconfined compression test that will yield the unconfined compressive strength. In these tests, a rock specimen in a cylindrical shape is placed between two platens and is compressed at a certain loading rate with a measurement of force and displacement. These force and displacement are later converted to stress and strain using the relationships you've seen in topic 1. The unconfined compression test is used to determine the stress-strain relationship that we plotted in the previous topic to discuss deformability and strength of material. You also have to know that for most laboratory testing, the conditions of testing are actually governed by standards and recommendations. This is for consistency reasons and to assure the quality of the results. When it comes to the unconfined compression tests, there are several criteria that have to be fulfilled. The first one pertains to the diameter of the specimen. It has to be at least 10 times the size of the biggest particle in the specimen. This is to ensure that the specimen we are testing is representative. Then, slenderness of the specimen matters, and the height should be 2 times the diameter, not shorter, not longer. So the third criterion concerns the faces of the specimen. Because the specimen is compressed between platens, the faces have to be flat and parallel to certain tolerances set by the standard. And finally, there are some conditions regarding the loading rate, that is the speed at which we load the specimen. If we go too quick, we're going to have dynamic effects and the results might be flowed. When it comes to the tensile tests, things are a bit more complicated because you can imagine grabbing on the rock specimen and pulling is not exactly easy. The grabs could slip, and you could also crush the specimen as you try to grab it. But an indirect method has been developed. It's called the Brazilian test or the indirect tensile test. And what happens, you can see on this picture, the cylindrical specimen lay flat on its curved surface with the flat surfaces being vertical. And the specimen again is placed between two platens. And as the load is applied, this load is distributed along a line on the curved surface, and that splits the specimen in 2 halves as the load is increased, as you can see on the video. You might wonder why this compressive action on the specimen might give this information about tensile strength of the material. This is in fact illustrated on this picture to come. What we can see is that loading the specimen in this way results in very localized compression across the diameter of the specimen, but about 80% of the diameter is actually subjected to tension, and the specimen does fail into tension, hence providing information about tensile strength. If you would like to know how we can compute the tensile strength from the load actually applied on the specimen, I invite you to consult the document provided in the additional resources. Again, the testing conditions for the Brazilian test are governed by standards. We have a condition on the diameter that has to be more than 10 times the size of the biggest particle on the rock, with typical diameters of about 50 millimeters. The length of the specimen has to be half the diameter, and there are conditions on the loading rate as well to avoid dynamic effects. Finally, the shear strength of rock specimens can be inferred from triaxial tests, also called triaxial compression tests. The principle of these tests is to have a cylindrical specimen subjected to radial confinement, and after this confinement has been established, we start loading vertically the specimen until failure. Again, the conditions of these tests are governed by standards or recommendations. On the left of this photo, you can see the base of your triaxial cell, which includes a pedestal on which the specimen sits. The specimen also has a loading cap on top of it. On the right of the photo, you can see that a bell has been placed on top of the base of the triaxial cell. That is used so that we can fill the bell with water. The water will be pressurized, and that pressure of water will provide the confinement to the specimen we were talking about earlier in this topic. You can notice on the left of the photo that the specimen is placed in a rubber membrane. That is to prevent water from getting into the specimen. The black lines are actually O-rings, that is little rubber bands holding the membrane tight around the loading cap and the pedestal so that water doesn't get in. Through the top of the bell passes a piston. The piston rests on the loading head that is on top of the specimen, and the piston is used to exert a vertical load onto the specimen after the confinement has been applied. In fact, the triaxial test is typically conducted in 2 stages that I will explain now. So in stage 1, the water in the bell is pressurized and the pressure applies a confinement to the specimen on all outer faces of the specimen. You can see on the left side of the figure, confinement is applied radially, but also on top and bottom, because the pressure is applied on top of the loading head that transfers to the top of the specimen, and the same thing happens at the bottom. In a later stage, stage 2, a vertical load F is applied through the piston, and that creates an extra stress onto the specimen. You can see the resulting stress, sigma 1, plotted at the bottom of the specimen on the right-hand side of the figure. Sigma 1 equals the initial stress, sigma 3, plus the force divided by the cross-sectional area. So during this stage, F is increased gradually until failure is reached. During this time, this confinement, sigma 3, is kept constant. The typical failure pattern in triaxial tests is characterized by an inclined band, as you can see on this picture. This is called a shear band, and we typically observe the top part of the specimen sliding on the bottom part of the specimen. After one test has been performed, we repeat the experiment at different values of confining pressure, each time with a new specimen, and that will help us to get different values of shear strength. Remember, we said in a previous topic, shear strength is not unique, but different tests should be performed at different confining pressure. When all these tests have been performed, we can plot the data as per the figure you're seeing now, and that gives us a failure criterion where we have all the shear strengths plotted against all the confining pressures. The general trend is a non-linear increase of shear strengths as we increase the confining pressure. The standards for testing of rock material have been produced either by the International Society for Rock Mechanics, called ISRM, or the American Society for Testing and Materials, ASTM.